Welcome back for the second talk of the day by Hendrik Weber. Hendrik, are you with us?
I am indeed. Can you hear me?
Okay, yes, loud and clear.
Perfect.
You may.
Okay, excellent. So I go? Yep.
Okay,
right.
Perfect. You may start.
So good morning or good afternoon here in the UK. Welcome back to the fourth of my lectures on interacting particle systems and stochastic PDEs. Many thanks also to Luigi, who has showed me how to make you bigger, so I can actually see you not only in the small corner of my screen, but I see you much bigger. So it's making me feel a bit less lonely. Thank you. Let's go into it. Let's just get started. Perhaps just organizational thing. So I started now at 20 past. Can I go until 20 past because you told me I had an hour, or should I?
Sure. You may.
Okay, good. All right. So last time, I told you about this diagonal scheme to prove convergence in law of this Kac-Ising observable here. So these locally average spins to the SPDE. So with this, we introduced this auxiliary parameter delta here, and that allowed us to reduce the proof of convergence in law here of two objects that don't a priori live on the same probability space to this pathwise stability analysis, where we just needed to prove here if you have this extra delta parameter. Let me just remind you here, this was an auxiliary object that we had constructed just by regularizing our noise on a scale delta, and so now we just need to show that these things are close, but uniformly close in this parameter gamma. So gamma, if I remind you, is the parameter that goes to 0 ultimately. I just wanted to just repeat this parallel to something that many of you may, I mean, that's at least where I learned about this first, is in contraction principles and in the proof of large deviations. And this is, for example, developed very nicely in the second chapter of Deutschland's Troops book.
So I have a question.
I just closed the window because it's quite noisy outside. I'll be back with you. Okay. They're doing gardening. There's gardening work happening outside, and there's a lawnmower, which is a bit noisy. I'm not sure if you could hear that.
Not really.
Okay.
Yeah. Okay. So, Hendrik, may I ask a question?
Absolutely, please.
So, in this diagonal scheme, when you're basically, I just want to understand that. So you're trying to take advantage of the fact that the solution theory has been already developed for the limiting object, and you have a solution operator. Am I correct on that or not?
Okay, let me perhaps just go back if you want to how it was yesterday. If you don't, oh, what happened now? Sorry, my thing just, yeah, lecture 3. Let me just go back to what we did yesterday on this bit. So it was here, right? So ultimately, what I wanted to prove here is you have an observable F, and you want to compare the observable acting on your particle thing or the rescaled particle thing to the limiting thing. And now we just do a triangle inequality. Basically, we compare the F on the particle thing to this auxiliary thing, which solves on the same probability space, solves something with regularized at scale delta. Then we do the same thing on the probability space where the Gaussian noise lives, and we compare these two things. And then we have the thing in the middle. Okay, so I've just used triangle inequality here that I can certainly do. And of course, the point that I already tried also to make yesterday is a priori, these things, of course, do not live on the same probability space, or at least, I mean, I'm sure you can do some abstract measure theory argument to put them on the same probability space, but it's not completely canonical how you would do that. And so now, but here they are. So these are coupled naturally, and you can, instead of taking the absolute value of the difference of expectations, you can actually take here the expectation of the absolute value of the difference. And then here, you do this jump from one probability space to the next, and then here you're again working on the same probability space and can put the absolute value under the expectation. And so the convergence of this thing going to 0 is cheap, because here you it's a bit similar to what you do in large deviations when you prove, for example, large deviation for solutions of SDEs. The mapping that maps the Brownian motion to the solution of a SDE with multiplicative noise is not continuous. And so you cannot directly do it, but if you do a continuous approximation, say you regularize your noise a little bit, then you use the cheap contraction principle. And it's sort of the same here. So for this thing here, you say, well, okay, this approximation of the white noise converges to white noise by some martingale CLT. It's an immediate argument. It's really automatic. But then if you allow yourself to regularize it and then solve the equation with this regularized noise, then this mapping is continuous. So you just use some contraction mapping. So this is for free, basically. And then what you have to do is only to prove that these things go to zero. And now it's just, you have to be a bit careful what is the order of limits and in which sense you have to do it. So we let first this gamma go to zero, then this term in the middle here just goes away for any fixed delta. And then we let delta go to zero after. And then what this amounts to is that you have to prove estimates of this thing going to zero, but uniformly in this gamma parameter. Does it make sense, or was it more of an answer than you were looking for?
Well, actually, you answered my question in the middle. Maybe I didn't formulate it correctly, but I was worried about the third line now, because the third line looks to me difficult because it involves knowing that the regularized equation goes to the solution of the equation.
I mean, it's even worse than that, because I have to, this is basically the theory of regularity structures, right?
Exactly.
And it's even worse than that, because I need to now do the same thing on the gamma and on the level of the gamma equation, which means the real work that I have to do is I have to mimic the theory of regularity structures on the level of these particle models. So not only do I need the full theory of regularity structures, but I actually have to develop it now for these discrete things. So it's if you want it reduces, it's very different in spirit, the analysis that we do from what, say, you and Patricia do. It really is a numerical analysis exercise, if you want. It's a stability analysis for the theory of regularity structures. If you put it on if you do an odd discrete approximations where you don't work with Gaussian noise, but with some jump noise. So I mean, yes, I agree with your suspicion, and it's even worse than that. Thanks. But I mean, okay, I mean, this now goes back. So this is exactly the kind of analysis that the theory of regularity structures was built to provide us with. And this is just the recap. So in the theory, always the analysis of an equation, or I mean, the main theorems that are stated in the theory of regularity structures are actually typically such stability results where you have a reasonable approximation, delta regularization, and you want to prove that this reasonable delta regularization converges to an object. That's actually typically how results are stated. And the proof of these things typically consists, as I said yesterday, of this probabilistic step, where you do a perturbative approximation of the solution, and the analytic step, where you use deterministic tools to bound some remainder. And so these are, I mean, like Schauder theory and reconstruction map. And similar for the stability analysis that we now have to do on the particle level. So we have to, in the first step, we need to do an approximate Gaussian analysis, as we just said. And let's say the second part is sort of, I call it the numerical analysis exercise. And I'm going to focus in what I did already yesterday and what I want to do today again on the first part. And for the second part, you can, for example, see this very nice paper by Dirk Erhard and Martin Heira from a few years ago. I mean, they developed this very systematically, and we've used actually their analysis for our second part also. So here is the probabilistic step, and this is what I already told you yesterday, and I've just restated it here, but I've used the notation, which is more in line of what would be done in regularity structures. So we needed, in the analysis of the 2D case, we needed these three things, but I've not used this notation. So last time I told you, I think last time I called this one here Z, which is just you take your noise and you apply the inverse of the seed operator with a mass, because I like to work with stationary objects on it. And the only thing that I do now here is on the left, I use this regularity structure notation. So I introduce this tree to denote the objects, and I act on it with a pi x operator. And I mean, okay, don't worry so much about it if you've never seen anything like this. This is just basically a definition of this thing. The only thing, again, for experts that I want to say, I mean, in regularity structure, of course, you have always this dependence on the base point, but this object here does actually not depend on the base point. And that's also why in 2D, you actually don't need regularity structures. And I should also say, I mean, of course, here I'm evaluating things at y, and in reality, you have to really put a test function here in order to make sense of this. But then in reality, we're always going to deal with a particle approximation where we can evaluate things pointwise. So I'm actually allowed to do that. Okay. And so this is the second object that we had. So this is the square of this object, and I had to do a contra term, and I use this shorthand notation here. And then we had this object here, which was the cube. Which, well, was this renormalized object, this thing cubed with the, and I will actually tell you later in this lecture where these things actually come from, so why it has this form. And so these are the things you need in 2D. And in 3D, you have additional symbols, and I'm not going to give you the precise definition what this thing is, but just panoramic. For this tree, for example, you will get this one. So this part here corresponds, if you want, to this bit of the tree. And then indeed, this actually then has positive order. So you do get an X dependence here. And again, for people who don't know what I'm talking about, please don't feel worried. I will not talk about it more after. And then you have to multiply it with this object here, which corresponds to here. And then you get an extra renormalization. But again, I mean, this was just panoramic and to tell you, kind of to give you a feeling there is something that I'm brushing under the rug. And if you don't know what I'm talking about, then don't worry about it. But just be aware there are some things that I'm leaving out. And but just to kind of define the target for us, what we need. So for each of these objects here, we associate an order which is very closely related to the regularity of the object. But it's okay. Let's not discuss it further. And in 2 dimensions, this is always 0 minus, so which means something which is just below 0. And in 3 dimensions, these are these values. And what we need in the probabilistic step, just to define the target for our analysis, is that this object here that we just defined on the previous slide, if we test it with these rescale test functions, and those I had defined yesterday. So this means you take a local average at scale lambda around a base point x, then you get this bound. Okay, and this I had actually told you about yesterday. So this is on one of the slides yesterday, I had given this estimate in the special case of z squared and z cubed, and these were always logarithms, but yeah. And so this is the typical thing that one needs in this analysis. This is the typical output of this first step that is required. And now, if you want to actually go one step further, you don't only want to have a solution theory, you additionally want to have the stability analysis that I was referring to. You actually need what we really need. Well, I mean, what's the real goal without any cheating is to prove that if we look at this thing now if we construct an analog thing for our particle model, and now we look at the delta regularization of that, and we look at the same type of order bound for the difference on the same scale here. And then we want to have a bound which is uniform in the gamma estimate, and that should go to 0 as delta goes to 0. So is this clear as a definition of what we really need? So I mean, this is just to going back. As I think Luigi was asking me yesterday towards the end, kind of what am I actually doing? What is the real goal? And what are we aiming for? So this is what we're really aiming for. Now I'm going to, from the next slide, go back to what I'm actually going to show you, which is a slide which is a bit weaker than this. But just, to just link it up cleanly with where we were. All right. And so now in reality, these bounds are now obtained always by moment estimates. And that's already where I went to already yesterday. And then these are upgraded with some Kolmogorov type argument, or if you want, Sobolev embedding. And so what we want to do here is, that's already started with yesterday, was the second moment estimate. So this is basically the same bound that I had just stated before. I'm not going to talk about the stability with the difference of terms. I'm just going to talk about the order bounds themselves, which already contains actually really the real difficulty and the most interesting bits. So I think if you understand this, then you're pretty good. And in the Kac-Ising case, where we will want something very similar, just with a gamma here. Okay, so for this with this, and this already contains the key difficulty. I mean, then there's a bit of post-processing needed, but I don't want to go into that anymore. So then what we did yesterday in the analysis of these things is I did a quick primer on Gaussian analysis or iterated stochastic integrals. So I reminded you, so we put ourselves in the framework. This is really just like a bit of background material on Gaussian probability spaces and stuff that's useful there. So I had this notion of a white noise, which is defined on over some measure space and defined on some probability space. And then we had defined these iterated stochastic integrals, n-fold stochastic integrals, and the point of the definition that I made is that this is defined by an approximation that cuts out the diagonal. And you should really think of this as, if you want, an iterated Ito integral, which also Ito integrals kind of don't see the diagonal, right? You always look into the future. And then if we do this, we have this, if you want, generalization of the Ito isometry, that you can write down the variance of such a multiple stochastic integral, the n-fold stochastic integral is, I mean, either bounded by if you're for general f, but if you impose symmetry on your arguments, then you actually have here that this is equal to the, well, up to a combinatorial factor equal to the L2 norm of L2 norm squared of the function f. And we call Hn is the image of this n-fold integral. So this is the so-called nth Wiener chaos. And this gives a nice decomposition of the probability space. I mean, again, for people who have never seen this, and if this seems very abstract, if you think about the easiest possible case where my white noise is sort of a white noise over one point, which is nothing else but a standard normal distribution, then all I've done here is I've set the fact that L2 over a standard Gaussian has an orthonormal decomposition into Hermite polynomials. Okay, so I've just used, this is a very fancy way of saying that the Hermite polynomials are an orthonormal basis for Gaussians. Okay, so this is kind of an infinite way of infinite dimensional way of stating it, but the core of this result is just that. Okay, and then so there was a price to pay for this cutting out of the diagonal. So we had sort of this Ito type formula. If we square, for example, these integrals, then if you naively assume some kind of Fubini, you would just assume that if you square a single integral, then you get a double stochastic integral. But as we had cut out the diagonal, we get this extra term which keeps track of the diagonal, so that can't go away. And I had argued, I mean, I had kind of done this bit hand waving argument with approximation here. Well, if these are elementary functions, then you have here this thing that behaves like the stochastic integral, which cuts out this bit on the diagonal, but that we can't just, I mean, it's still there, the bit on the diagonal, so we can't just ignore it. And then we put it in a second term. And the second term here gives me this deterministic contribution. And there's a similar identity for, I mean, there's similar identities for more complicated expressions but the only one I'm going to use here is the cube. So for the cube, we're going to get a threefold stochastic integral, and we're going to get a similar term for diagonals. So it's a 3 in front here because there's 3 different ways of pairing 3 coordinates, right? So this is what this 3 means. We can either have x is equal to z, or x equal to y, or y equal to z. So this gives me that. The point which is actually worth noting is, I mean, there could also be a term for where all 3 are the same, but that actually disappears in this context. So we don't have that. We only ever have to worry about contractions of 2 variables, not 3 at the same point or 4 at the same time. You can kind of imagine that this thing would then be too small, which is convenient because it's not true, for example, in the particle case anymore. So now let's go back to the stochastic heat equation. And I want to show you a little bit, I mean, again, I told you I want at the very end show you a bit how we mimic the construction that is very convenient in this Gaussian case, in this particle case. And I'll have this only in the last 10 minutes for today, but I want to actually explain you first what I'm trying to mimic. So what is the nice Gaussian analysis? And I want to kind of show you, well, this is really cool and actually pretty easy and convenient to do. So this is again what we had yesterday, this kernel representation. I have here my space-time white noise. I have here my kernel. I'm going to now use a bit freely this spatial variable, this z always as a space-time variable. Okay, so z is always an s and an x, and I'm going to treat them as a single space-time variable, ignoring that they're actually kind of different. And so of course this is nothing but, in this notation of this iterated integral, just the one-fold stochastic integral of this kernel k around z, okay? And the aim is now to understand or get an estimate on the z squared. And I mean, okay, everything is too irregular, so what you should really think of, what I'm doing is I regularize everything on a very small scale epsilon here, and I'm going to put this actually on my kernel, so I'll cut off the kernel like a little bit away from the origin, and everything is smooth. So then these things are smooth. I'm legally allowed to write this down. And then I want, of course, to get estimates that are uniform in this epsilon parameter. But I will mostly skip that in the notation, and I'll just pretend that I'm allowed to do everything I do. Okay, so yeah, I hope that's okay. Okay, let's just do a calculation. So the aim in 2 or 3 dimension is we have this z epsilon here, we square it, and now we test this against a localized test function around a base point z, okay? And now we want to calculate the variance of that thing, or the expectation squared. It's actually, yeah. So now let's just go for it. Let's just calculate it. So the first thing is, of course, when you calculate squares, it's always a good idea, or almost always a good idea, to just double the variables. And this is deterministic, so I'm pulling it out. So this testing I write as an integral, this, and by doubling the variables, it becomes a double integral. So I have here the phi around the base point, around the same base point, but here I have another running variables, they're different. And here I have the expectation of the random object that is here evaluated at these two different points, once with a z here and once with a z bar. Okay. And here I take and again, here I'm just using the definition. This was just the first iterated integral of this thing here, and now I square it. And I do the same thing here. Okay, so I've just, this is the idea, you have done nothing. And now I want to use my generalized Ito formula that we have just seen on the previous slides. So this thing here is the square of a stochastic integral. So let's just write it as the double stochastic integral. This is kind of, if you want, my formula for Bini that I had before, where I now have a double stochastic integral and I have a kernel, but I have to integrate it in the white noise in two different arguments. So I put this blue for one argument and red for another argument, and that I will call A2, this object. And then, but then there's the contraction term, and the contraction term is this one here. Okay, and I'm going to call this A2. And this is just where, I mean, right, these arguments are just become the same. So this is this diagonal estimate, and this is just a number. And actually, this is actually the expectation of this whole social thing, because this thing has expectation 0. Okay, so I've just used the this kind of Ito formula, if you want. And now let's go in for the first term. So let's just calculate what is the variance of this first term. So I will plug it back into this integral. Here again, my kernel is evaluated at same base point but different running variable, integrated against here, and then I've just plugged in my definition. And now I use now it's nice. I know that this expectation we have just, this was the first tool that we had seen. This is the expectation of a double stochastic integral, and I can actually just use, I mean, this two isometry, right? So this was the second point of what we had here. And so what I'm doing here is here's my combinatorial factor. This was the 2. And then I just have to calculate this A2 norm, and I'm writing it here like that. Okay, I must admit I'm using a slight polarization here. I'd only proved this for the variance object, and here I'm writing it for the covariance of these two things, but okay, I hope that's fine. So then you get this this expression here. So you have here the kernel evaluated at this base point z with the first argument, and then here the one with the second argument, and then you have to here contract these arguments, and you have to contract these arguments. Okay, and okay, I mean, this possibly doesn't yet, like here I'm also just reminding you what this kernel actually was. Okay, so this is a principle at this point. Good news, I have got an integral and I can solve it. I mean, I can estimate it. So I've just reduced the problem of calculating this complicated expectation to just calculating some integrals, and that could be I mean, that could be seen as something now pretty benign. And actually, it will turn out in this case, it is pretty benign. But I'm going to show you sort of a machinery that admittedly for this integral is complete overkill. Just, I mean, to give you an idea, this is the simplest possible tree that ever appears in this kind of business. And in general, we'll see much, much, much more complicated trees. So I'll give you a bit of a framework and way in which to think about these expressions that will also allow to look at more complicated expressions, even though here, admittedly, it wouldn't be necessary. So the first thing that I like to do is to draw a picture, because I can kind of not really, I mean, expressions of this type with Z1s and Z2s and whatever, I'll get terribly confused because the different Zs, and I'll always get the indices wrong for sure. So let's just write this whole expression here. Let's kind of find a nice graphical representation for that. So, and this is what this here means. So let me explain this picture a little bit. You have here the base point Z0 around which we test, which I draw here in yellow, and here on the right also in yellow for the second one. And then I connected to this running variable Z here with this kernel phi lambda. This is what I've done here. And the same thing I do on the right-hand side. So this bit, this kind of corresponds to this part in the diagram. And here I connected to this different variable Z, that bar, okay? And then here, I have now a new argument, Z1, which is here, and I connected to this one with this, according to this kernel, okay? So this is what this edge here in the graph means. And then I have the same thing here. I have my Z2 variable here, and I connected to this one with this kernel. And now the same thing on the side, right? This kernel here connects the Z1 to this one. and this kernel here connects from here to here. Okay, so I mean, you may disagree, but kind of if you understand what it means, I find actually such a diagram much easier to read than this complicated integral, and actually it's also easier to draw once you're kind of comfortable with translating it. And it's also easier to keep track of which argument is what, because again, I mean, if I try to copy this from one line to the next here, I promise that I get at least one of the indices wrong. So, I mean, you may be more diligent than me, but in a long calculation, it's very painful. These diagrams are actually quite convenient. And sort of what I want to show you now is a bit of a formalism that you can analyze these integrals and staying on the level of these integrals, of these diagrams as much as possible, and trying to write down ugly expressions like this as little as possible, okay? So the aim for now, I want to show you just a kind of a neat formalism, or I mean, a way to think about it that works mostly on these diagrams that kind of denote, if you want, generalized convolutions. Okay, so the first thing is what kind of information on our kernel do we actually need to keep track of? And here, the main important question is actually just, I mean, the kernel is here, this Gaussian heat kernel. And I mean, of course, I mean, all of you are used to these kind of pictures. And of course, I mean, the only property that we're interested in here is that this kernel is smooth away from the origin. So there's the only singularity that we care. I mean, that's the only thing we care about is the singularity. How does this behave as t goes to 0 and as x also goes to 0? And in which way does it blow up? I mean, it converges to a delta Dirac, but in which sense? And you can check. I mean, this is actually something that I remember when I saw it for the first time, I found a bit surprising. But the only thing that's actually needed here is that if you define this parabolic distance from the origin, so square root of t plus the absolute value of x, and I mean, you have this different scaling that due to the different role than t and x play in the heat equation, this blows up as these things go. I mean, you have this estimate like that this thing is bounded by 1 over z to the d. And I mean, I remember when I mean, sorry, I should have, that was bad notation. I should have actually really written here d of z and the origin to be consistent with what I had above. Sorry, that was okay. And I mean, this is perhaps a bit surprising. I mean, again, at least when I saw this for the first time, I found it a bit odd to think of a parabolic heat kernel in this way. You may be used to thinking, for example, of a Gaussian, of the elliptic Green's function, right? I mean, if you an estimate like that is bounded by x to the minus d plus 2 or something like that, right? This is probably an expression that you have seen.
Hendrik, we have a question from the audience.
Yeah, there was a question in the chat, which means that the question is, do you mean for t small? Sort of, yes. I mean, okay, yes. Let me answer that question in a second. So, if you don't mind. So this is, you may be used to this kind of expression for, say, elliptic functions, but I was at the time a bit surprised actually to learn that one could just write the same thing for this parabolic kernel, and it's a much more elliptic way of viewing the heat equation, which one may choose to adopt. And it looks even more like that if this is a d, which is the spatial dimension here, but it's actually not a bad idea to think of space and time and to introduce an effective space-time dimension, which is the spatial dimension plus 2. And 2 counts because time scales different from time behaves different from the spatial dimension. So this 2 here stands for time, and time counts twice because it scales different from the x. So then what you get here is that this kernel here is a kernel of, if you want, of order has a singularity on the origin that blows up like minus the effective dimension plus 2. And so it makes it look very much like the elliptic Green's function, actually, if you view it in this way. And so there was a question in the chat about should t be positive? And I mean, yes, of course. In this mild formulation that gives me the equation, of course, I only ever evaluate this for positive t. So yes, t positive, but of course. Actually, one could even be more brutal here. I can extend, of course, the heat kernel to negative times by just saying it's 0 for negative times, and then the convolution identity still holds. And the only thing I'm ever going to use is that you have this estimate if you want with an absolute value here. So I'm not actually in this regularity analysis even going to use very strongly that it's 0 for negative times. I don't really necessarily want to extend k to negative times, but I could. And I would just extend it by 0. And then I'm just saying I don't really need very much. In this kind of regularity analysis, I don't use very strongly that it's 0 for negative times. It's really just the blow up of the kernel. And this is just to make it look more elliptic if you want. So now this is the first information, but you see, I hope you appreciate the amount of complexity that is already reduced. I don't have to write down this ugly, okay, this complicated, slightly complicated looking kernel. I just need to have this bound on how it behaves at the diagonal. That's the only information I really need here. And one of the nice things that is pretty easy to check and which is convenient when manipulating integrals of this type is that about convolutions, right? All these integrals, again, it's a pretty simple integral that I had here, but they are much more complicated expressions. So that it's worth to think about things a little bit systematically. So if you have two kernels with a different blow up, then their convolution is again a kernel of the correct order, and and what happens is that these blow up rates add, but you gain once the effective dimension. Okay, this is something that you can convince yourself. This is and the proof is not very complicated, but what is interesting is that you have two conditions here for this to be true. On the one hand side, you need each of these kernels here to have a blow up which is better than the effective dimension, and that is kind of clear because you need things to be integrable. Without this, the convolution doesn't even make sense. You can see it actually here in the proof, and you need the sum of the regularities to be better than minus the effective dimension. And you can see it actually if you convince yourself here in the proof pretty easily. You need this condition here to even be integrable locally around x or around the origin, and you need the other condition to be integrable at infinity. So it's relatively easy to convince yourself of this. And the other thing is now we want to just once again. So we use the graphical notation for stochastic integrals. So this is, as we had already said, this is kind of corresponds to white noise, and I integrated up once. This corresponds to this, and the z's. And for the z square now, as we had seen before, we have this chaos decomposition. This is an iterated stochastic integral, which we write like that. But then we have this contraction, which comes from here. And for the 3, you have here this iterated stochastic integral of threefold, and then you see that you have here in this contraction, you can see immediately in this formalism that you have to contract these two, and it gives you that. So if you want, you could write this as could also write it perhaps more conveniently as this. And the 3 you can already see comes just from the fact that you can choose to contract that with that, or that with that, or that with that. And now we're going to use this to do again exactly this graphical analysis. So what we're going to do is, so this thing here symbolizes this iterated stochastic integral as we had there, and now we see that this expectation that we had to calculate can be written as twice this, the integral that we had seen before, and the only information that we need is that we have a kernel here of order minus effective dimension plus 2. And now we do with this convolution estimate a replacement. So this bit here stands for one of these convolutions, which says that well, I have here a kernel of minus the effective dimension plus 2, and here minus effective dimension of 2, and both of these conditions are satisfied. So that if you check, you have always individually these things are better than minus effective dimension, and the condition on the sum here is true for every dimension which is bigger than 2. For 2, actually, it's not. You have a log divergence, but okay. And then what you see is you can do this replacement here, and you get here so basically the only thing I've done, I've calculated the inner integral in here, and then you see you have two singular kernels here which you multiply up, and then you just add up their singularities. So you have a minus effective dimension 2-dimension effective dimension plus 8. And now the second estimate that we're going to, sorry, what did I do now? So this is already had. So the second thing I'm now going to do is now I have to see how this behaves if I test against these rescaled things. And what is also, again, relatively easy to check, if you have here such an integral, and if this alpha is integrable, so that if the alpha is bigger than minus the effective dimension, then you get exactly the right estimate that you need. So what we get from here is now that this you get exactly the estimate in lambda to the minus effective dimension 2 effective dimension plus 8. And this actually works for all, I mean, you can check here, this works for all dimension less than 6. And so what we have proved with these two really simple lemmata, one here is this one, and one was this convolution estimate, is that this this part of the stochastic integral here, we get the correct order bound in lambda. So in 2, we get this log divergence, and dimension bigger than 2, we get here minus effective dimension 2 effective dimension plus 8. And in particular, in dimension 3, 4, 5, this will, if you translate it back into like the real space-time dimension, this is a minus d plus 2. So now let me just show you that this is actually quick. You can do this graphical analysis very easily. You can just say, well, let's do the same thing for the third Wick power. So the algorithm now goes very easy. You just glue them together. So you get the 6, you double the variables and you glue it. Then you check that the replacement is okay, which we have already done. So all these here now can be replaced by these. The orders, we've just worked them out. You add up the orders and you just check the condition and you're done. So what you get from that is, for example, for the third Wick power, that you get this blow up for dimension less than 4. And this, for example, gives you regularity 0 minus in 2 dimensions and minus 3 over 2 in 3 dimensions. So, I mean, once you're a bit familiar with this, this is super convenient. And you see, you can just do the calculation in a few symbols, just check a couple of integrability conditions, which is much quicker than writing down ugly iterated integrals. So this was, I mean, I hope convincing that graphs are actually practical. So the summary is now that this graphical analysis is quick, and the convergence of all the terms depends on the dimension. In particular, we can do the second Wick power here as a space-time object in up to 6 dimensions, and we can do the third Wick power here up to 4 dimensions. And we also have this neat thing that negative regularities add if you want. So in 2 dimensions, everything here has order 0. In 3 dimensions, you have here regularity minus a half, minus 1, minus 3/2. In 4 dimensions, you would have a minus 1 and a minus 2 here, and this thing doesn't exist anymore because the integrability condition on the diagonal was violated. 5 dimension, you would have minus 3 over half, you would have minus 3 here, right? So you would, I mean, in a sense here, you're not in general allowed to multiply distributions of negative regularity, but if you could here, then the negative regularities should add, and this is what this table here reflects. So this is the analysis of these terms. But of course, now we have still ignored these contractions. Okay, so there's this term that we haven't yet spoken about, and this term that we haven't yet spoken about at all. And now here we see the problem. So this is actually where these infinities come from. If you do if you can do the graphical just power counting analysis, you see this thing here, this convolution here should behave like that. And this is integrable if and only this is true. So this means effective dimension has to be less than 4, which means real space dimension has to be less than 2. So it doesn't work. I mean, this just diverges. This is exactly our log divergence in 2 dimensions, and the epsilon to the minus d plus 2 divergence in 3 dimensions. Okay, so this is the leading order divergence that you have in all these bits. So this is the thing that we wanted to get rid of. And the solution, of course, as you may not be surprised to hear right now, is we just trash these terms. So what we've basically proved with now is that we just throw these terms away. So this thing alone wouldn't converge, but here's the counter term that you have to subtract. And then the difference of these things actually does converge to a random distribution of the correct regularity. And for 3, there's this Wick counter term, and I certainly should write a 3 here, that converges again up to the right thing in 3 dimensions. And the limit is called Wick order or renormalized square or cube Zn. And this is indeed where these infinite counter terms come from. Sorry if I was going a bit quick on this analysis. I think this is now a good point to take a breath and ask you if you're still happy with me.
Let me see if I understand what you're saying. So, for example, for the cube, you are saying that the iterated integrals converge, yes, but not the integral to the cube, because it's not the same thing. You have to take out the diagonal terms to pass from the integral to the cube to the iterated integral.
Correct.
And if we were doing just here, if we were doing just Ito calculus or Stratonovich calculus, these terms cancel or do not cancel, but they are kind of embedded in the stochastic calculus, right?
I mean, I'm not sure if I understand completely what you mean by doing Ito calculus. I mean, I would say this representation of stochastic integrals is Ito calculus, no?
Yes, yes. I was saying that if you, instead of Ito, you do Stratonovich calculus.
Right. I mean, I think if you want to draw this analogy, then what I'm doing is probably a bit like an Ito calculus, and as a consequence of doing Ito calculus, you have to use Ito formula rather than chain rule if you want.
Mm-hmm.
And the price to pay is that you get these extra terms on the diagonal, but the benefit is that you have, when you have expectation 0 and you have Ito isometry, which of course you don't for Stratonovich integrals. So
Yeah.
So for calculation of variances and expectation, Ito is more convenient than Stratonovich. I wouldn't know how to do that kind of calculation with a more Stratonovich type calculus.
Also a question. I was wondering, for the choice of the base space. So we never used the convolution, the fact that these kernels are transition invariant. Let's say just the only technical ingredient is this on diagonal upper bound of the kernels, right?
Yes, I think that's true. Yeah, I mean, in more complicated examples, one needs more on the kernel. One needs to know that also derivatives behave in the correct way. So it's a bit like what you do in harmonic analysis, where you, right, I mean, you have these singular kernels and you always want the singularity behave like distance from the origin to the minus dimension. And then if you take the first derivative, you're allowed to have an extra -1, and another derivative, you have -2, and these kind of things. So the real conditions that one puts on kernels in more complicated integrals are often more of this type.
Okay, but we'll see later, or
not
they appear later?
Not in the next 10 minutes, I'm afraid.
Okay. Thanks.
Yeah, I think the analysis that I'm doing here would certainly work if you didn't have translation invariance, if that's what you're saying. Translation invariance is convenient. I think it's definitely convenient to make certain calculations easier. I don't think it's necessarily completely required. Okay, good. So this is this analysis of Wick powers in the Gaussian case. And if you want to do now the stability estimate that I told you initially, then what you have to look at is two differences of kernels, and what you typically I mean, it's not such a complicated modification. You can do it. So now what I want to tell you, before I go there, I have actually a little bit of literature. So, I mean, again, there's lots of references that do stochastic calculations of trees of this term. And I think what I showed you now is sort of if you want, an easy version of what is done in Martin's original paper in 2014. So there's decomposition into Wiener chaos, and to use graphs and facts of the singular integral kernels in the way that I showed you. That's all done in quite a bit more generality than what I discussed here now, but perhaps not so much more in Martin's original paper. And you could also have a look at these notes that I wrote a while ago with Jean-Christophe and Wagen, where we did something similar for para products. And so then, since then, the methods have kind of increased in sophistication and in complexity, because the number of trees, the more complicated the equations became, the number of trees has just exploded. And so there's this, the next level, I would say, is something that was done by Martin and Jeremy Costel. And they use some trick called Hebb sectors, and just have to check some geometric facts of the graphs, and then everything is for free. And then this has been pushed even further in this work by Ajay Chandra and Martin Hira, and that basically says that pretty much in pretty much any subcritical SPDE, all the trees you will be able to renormalize them. So this is a very, very strong statement. And let me perhaps also, just as a reference, give you a very recent preprint, which is quite nice, by Linares, Otto, Tempelmeier, and Tsatsulis. And they have a completely different approach to bounding these trees, which is very interesting, which is based on spectral gap inequalities, and is a bit more analytic and less. I mean, it's a different approach, and it's quite interesting. So if you're interested in this kind of stuff, have a look at it. So now what I want to tell you about in the next 10 minutes is what we do with Kac-Ising. So now let's go back to this Kac-Ising situation. So here I've just rewritten the equation that we had. So we had here, this is this rescaled locally averaged spin field. Here we had this approximate Laplacian. Here this extra linear term, the cubic term, some higher order terms that I'm not spelling out, and these martingales. And so now I want to basically, as I said, mimic this continuous analysis on this particle level, and I have to now first of all define these approximate models. Okay, and what we're going to do here is quite, I mean, in a sense, straightforward. So, for example, for this first tree, the linear stochastic heat equation, I'm just going to use the solution of this equation with this noise, and I'm going to trash all of that. Okay, so this means I can write explicitly using this mild formulation here. So here I have the heat kernel that goes for this operator. I mean, if you would like to think of it in other terms, this is the generator for a Markov chain, and these are the transition probabilities for that Markov chain. Okay, so it's something, and this is pretty explicit actually. If you want to see what this looks like, you have a very nice representation for the Fourier series of this operator, and you have a very explicit Fourier representation for this kernel. So this is pretty hands-on, and then you just solve this equation. I mean, let me perhaps just make a quick remark on this. So this is a convention. This was already used also in Jean-Christophe and my work a couple of years ago in the 2D case. And but it was not used if you look at the papers in the 90s by Pressotti, Rüdiger, Josef Fritz. And so they did something else, is they actually coupled this to some, if you want, some linear voter model. And the difference to what we're doing here is we're just solving this equation. But of course, this is not, if you want, an independent particle. This cannot be derived from sort of an independent particle model by itself. It's just, I need to know what the martingale is, which means I need to know what the original particle model really was. It doesn't exist sort of as an object per se. It's just an intermediate object in the analysis, and it's actually not a problem. You can just define it as just a bit of a leap of faith to work with such an object rather than introducing an independent particle model that you could just couple or so. It's I mean, it's technically actually not a different, and I find it more convenient, but I just want to say this. So what we do is so just that I told you here. So this is this transition kernel for the Markov chain that we control very explicitly using the Fourier representation. These are these jump martingales, and I had already told you here. So they have small jumps that we control very well. And the predictable quadratic variation is almost constant. Again, I mean, we had always this form a half plus something small. So that looks good. So in principle, this looks like almost a Gaussian process. And okay, I mean, here, just because in the limit we want to work with stationary objects, we have extended our noise to negative times, but that's a minor point. So this would be, for example, our choice of the approximate model acting on this tree. And then we do something similar for the remaining symbols. And actually, I mean, now I've been talking for 4 lectures, and now only in the last 10 minutes I come to the honest thing that we really been up to. I mean, this was the real work of this project, was to estimate these things as if they were Gaussian. So we had to now do a similar analysis to what I just showed you with this nice Gaussian calculus, Wiener chaos, and we had to do it in this case where these are, well, not quite Gaussian, and they're almost. And I just want to give you a quick panoramic impression of how something like that would look and the kind of difficulties that arise, and that makes it a little bit less nice than the Gaussian case. So let me just show you, for example, the tree that we just analyzed in a lot of detail in the Gaussian case, so the square. And okay, I mean, let's do it without renormalization first. So I'm just going to take the thing that I just defined here, and I'm just going to square it. Okay, so this is this would be if you want, the canonical thing without renormalization. And of course, ultimately, I will want to subtract some contour term, but let's see how this arises. And the first thing that I want to stress here, and this is something that's, again, for people who are used to Gaussian calculus, actually a bit counterintuitive, is that here I'm perfectly allowed to write down Fubini's theorem, right? because these martingales are jump martingales with a finite number of jumps on an interval. So this dm is a perfectly honest integral against the measure of bounded variation. So Fubini's theorem is absolutely valid. There's really no cheating involved if I write this like that. But of course, still, given that we ultimately want to kind of see how this behaves relative to something Gaussian, we want to pass to the given, it's probably a good idea to separate here the off diagonal part and the diagonal part. And so we do that. So I'm just right. I mean, I view this just as a massive double integral over space-time. This is of course a discretization in X, but I'm just viewing it as a massive double integral. So I'm just integrating now over space-time points off the diagonal. And then I have here this diagonal term. Okay, so this seems like a sensible decomposition to make, given that we want to go to the Gaussian limit. And again, you should think of, just in analogy to what we had seen, you should think of this corresponding to this diagram or this iterated stochastic integral. And this was this contraction term. So of course, this should give me my 1 over epsilon divergence, and this should behave well. Okay, so that's the hope. And so now one goes about it, and I'm not okay. I don't want to speak so much about this one. This one is actually then relatively benign. You can use it you can bound it by some suitable version of Buchholz's inequality. So this is you have an iterated you have an integral against the martingale, and then another integral against the martingale. So you iterate some BDG inequality, and you get what you want. It's a bit of work, but I don't want to stress it so much. So there's, I mean, this is okay. But I want to tell you a little bit what happens on the diagonal now, which is different from the Gaussian case. So what actually is this for a single point in space-time? What actually, so we have now here, we have the product measure of this thing. And now we have to evaluate it on the diagonal where these points are the same. So what is this measure actually? So let's just go back to this original martingale. So the martingale was the rescaled version of the process here minus this drift that makes it a martingale. So now for this product measure, this part here is absolutely continuous with respect to Lebesgue. So this doesn't see, the diagonal doesn't see this one, this disappears on the diagonal. So the only thing that actually matters on the diagonal is the jumps of this. So what this means is this expression integrating over the diagonal can actually be rewritten as the sum over all. I mean, you still sum over all points. And actually, sorry, I've forgotten in my scaling an epsilon to the d here. You sum over all points. You sum over all points, and then you have here just the jump at that time squared. Okay, so these are just the Diracs. These are just the Diracs, if you want, of this. And this, of course, is again an object that is well known in the study of these martingales. This is just an integral with respect to the quadratic variation. But this time, one has to be a bit careful. This is not the predictable quadratic variation. This is if you want, the usual quadratic variation, the one with these brackets and not the one with these brackets. And so now this object, again, I mean, I'm just showing you one of these things we had to fight against. And so this thing should now be, let me show you this. This thing should now be our leading counter term. So this should be exactly this log gamma inverse divergence in 2 dimensions, and it should be exactly our gamma to the -3 in 3 dimensions. Okay, so so we're perfectly happy to say this is a constant which diverges like that, we can throw it away. What we're not happy to say is this is a random variable which blows up and we throw it away, right? I mean, there's a big difference between throwing away a big constant and throwing away a big random variable. And this thing here is a priori not a constant, right? I mean, this is the predictable, this is the quadratic variation, it's a random process. So let's hope that we can do better. Let's say that this is not so random anymore. And then the first thing that one can do is, that's one of these standard tricks in this business, is that the difference of these quadratic variations is, I mean, there is a difference, but the difference again is a martingale again. And so this difference, you get it under control, so that's fine. So we're happy to now replace this by this quadratic variation. And this is explicit. We can actually write it again as this integral squared, and you have the c. And I mean, this was a point where we're saying we're great, we're there. This is done. This is because this is just a half, which is constant plus something small. And then at some point you make the painful realization, well, how small is it actually? Because you're basically multiplying it here with a 1 over epsilon or a 1 over gamma cubed. It's something better be pretty small if it's still small after multiplying with 1 over epsilon or 1 over gamma cubed. And this was, okay, perhaps, you may not be appreciating this now in this 30-second overview, but this was a point where kind of 1 year work in, we were panicking a bit, where we realized that, because it's not so clear that this is actually true, because we have here, this is a priori only a gamma cubed, and only gamma cubed measured in a negative distributional topology. And now it looked really ugly. And then we realized that you actually have to get some extra cancellations from here. And it was, and after playing a lot of tricks and doing a 15-page argument, it tells you that it's actually not 0, but it's a constant plus something that goes to 0. And the constant is okay. So yeah, again, I appreciate that you won't actually be able to follow this in detail. I just want to give you a panoramic impression of the real thing we had to do, which I think is fine, 2 minutes before the end of my course. So that's it. That's what I wanted to say. Let's just go to the kind of the conclusion of everything slides. So what we've done in this week is that I've showed you how to analyze these Kac-Ising models in this very particular scaling near this mean field critical value beta equal to 1. And I showed you that the limit is a nonlinear stochastic PDE, this 5-4 equation. And so then I gave you a quick primer on this limiting SPDE and showed you that this, in particular, I stressed that this needs renormalization. And this is, but on the level of the particle system, it's actually not something so scary. It's shifted just in a very small shift of this temperature that you have to zoom around. So in 2 dimension, you had just 1 plus this correction of order gamma squared log inverse, log gamma. And then in 3 dimension, it was this gamma 6, gamma to the minus 3. So it's really just a small shift from 1. And so then I told you that technically there's this nice diagonal trick that we learned from Martin and Dirk's paper that allows to reduce just to the stability analysis of the SPDE. And that's exactly what's provided by theory of regularity structures. And again, the real work of this big project, the key technical tool is to iterate all these diagrams. And I gave you a big, again, like a bit of more panoramic view of how this can be done in the limit in the Gaussian case. And then at the very end, I just showed you some of the difficulties that arise when you try to mimic that kind of argument in these like almost Gaussian analysis and these things. So that's where we are. Thanks a lot.
Thank you. Maybe we have time for one quick question.
Well, since lecture 1, I was worried when you said that the guy was 1/2 plus something small when you talk about this quadratic variation, because yeah, that's just even in hydrodynamic limits, it's not always so easy to bound that guy.
I agree.
And puzzle a little bit because usually, at least in hydrodynamic limits, what happens is that the way you bound that guy in the quadratic variation is because you first prove hydrodynamic limits, and that is what actually tells you that this guy is going to be constant. And then you go to fluctuations and do that and go to the next step. So it's a little bit of a normalization thing that. So, but here in what you're doing here, for example, the invariant measure doesn't play any role at all, no?
That's correct.
But you should have some a priori bounds on what your actual process do somewhere, no?
I think here is a different. Here it comes into play. What you like to tell me is that this Katz model is actually a cheat and not really an interacting particle model. So what is this actually, right? What you have here, this rate. Originally this had this form, right? You had an M. Sorry, you had here this magnetization, or here this H. Yeah, this was what it was, right? And the point is that here you have, if you do it this way, here you have the local averages already in the thing. And okay, if you want, our hydrodynamic limit here is 0, and we're looking around the fluctuations around the hydrodynamic limit 0. And the way this technically works is, so we now write this as delta times the rescale thing, right? And delta is small, right? Delta is is gamma in dimension 2, and it is gamma cubed in dimension 3. And so what you can, for example, do is certainly, say this is easier in dimension 2. Let me do it in dimension 2. This is certainly bounded by, if you're super brutal, you put bounded by 1 here, and here you just put this is bounded by, certainly bounded by the L infinity norm of h, right? And now this is bounded by delta times the L infinity norm of x. And now you think, well, this is at least in 2 dimensions, this is perhaps a bad idea because our thing is going to be a distribution, but it's just about distribution. It's of regularity 0 minus in 2 dimension. So and you have a Fourier cutoff at level say gamma to the 4 or something, and it's just diverges logarithmically. So by some version of Bernstein inequality, you just sacrifice kind of a gamma to the minus kappa, and you put here the distribution, the real distributional regularity of this thing. Okay, and now what you can do is, I mean, it's this typical argument where you use stability of the limit in order to deduce something for the approximation. You'd say kind of tau is the first time that x gamma in this negative Bezoff norm is bigger than say 10,000 or 1,000,000. And then, and clearly before that stopping time, you have this deterministic bound here. And then you prove that up to that stopping time, you're actually, I mean, this x gamma minus the limit is actually bounded by 1. But the limit is actually by some limiting argument is actually bounded by whatever, say 10. So hence your stopping time hasn't happened. That's roughly how the argument goes. It's very cheap. I mean, I appreciate that in hydrodynamic limit, you have to work way harder for this. So here it goes with a cheap argument like that. That's why you don't have to be worried so much. But of course, I mean, to not kind of sell ourselves so short. So in 3 dimensions, if you want to do the same thing, it's way harder. I mean, only actually, surprisingly, it works very well, except for this one bit with these constants, where we then had to get worried. And that's exactly where this happened. So in 3 dimensions, if you do the same thing, you're brutal. You put here, again, the L infinity norm of h, which is now bounded by gamma cubed times the L infinity norm of x. And now you realize that this is perhaps a bad idea because this is a distribution. You do your Bernstein argument, and then you get here, this is bounded by gamma cubed. And now you have actually the x minus a half, because this is not 0 minus anymore. So it's worse. So you actually then have a gamma to the minus 3/2 minus that you lose, but it's still positive. But now, of course, you don't have so much room, right? I mean, and now if you put this into some divergent constant that gives you bad extra factors, you start to worry a little bit. And that's where then we had to start to think about, well, actually, perhaps this thing also matters, and this buys us another delta if you view this as a local average. And yeah, this was this argument that I just told you.
Okay, so let's thank Hendrik for the exciting course he gave us. Thank you.